Hi, good evening. It is 6 p.m., but till now only one participant has joined. So we'll wait for a few more minutes to see if others could join us. Thank you. Good evening, and welcome to week 4 of the live sessions for the course Fundamentals of Additive Manufacturing Technologies. I am Sourav Goswami, a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. This course is taught by Professor Sajan Kapil, who is a faculty member in the Department of Mechanical Engineering at IIT Guwahati. This week, the lecture covered the stereolithography process, also known as SLA, and we looked at some of the subsystems, the laser beam, and the dynamics of various curing mechanisms for single bead, multi-bead, and also some brief introduction to the multi-bead multi-layer. Uh, it's, as had already been discussed, based on the classification of the subsystems. The 3D systems SLA, which was the first commercialized 3D printing technology, as well as the improved Zephyr model, use galvanometers as scanning systems. The shape of the UV light is in the form of a laser beam. So rather than a floodlight, which can scan an entire area at once, they use a laser beam to scan the entire region point by point in the form of various lines. The liquid is kept in the form of a vat. The build direction is typically in the plus Z direction. And in terms of recoating, the original 3D system SLA uses deep dipping, where the entire part is dipped into the vat of liquid, and then a doctor's blade or a suitable roller takes away the excess liquid and retains just the column of height, which is desired by us in terms of the layer height. Whereas the modified version, the improved Zephyr version, uses top fitting, where a head, which is full of multiple nozzles, deposits a curtain of fluid on top of the build. For deep dipping, as we discussed, we require excess amount of resin in the vat, whereas for top feeding or other mechanisms, the amount of resin needed for printing the next layer is just the limiting amount of the uh, volume of the resin column required. Now, just like any other AM process, even the SLA process can be divided into the pre-processing, building, and the post-processing stages. So during pre-processing, while we are still working at our computer, we have generated the CAD model or gotten it from the client. We orient it suitably based on our uh, criterion or based on the objective statement that is given to us. Based on such an orientation, there might still be the need for support structures for overhangs, and then support structures are generated for us wherever required. Of course, as we are aware, most modern CAPV packages will themselves suggest what are the regions which are vulnerable and will require support structures. Then it is up to the expertise of the engineer to select whether at all support structures are needed or not. And then planar slicing is performed for the case of stereolithography. For some more recent or advanced applications, even conformal slicing may be used. Now, how the build process itself progresses is by the motion of the table. We know that for this case, for SLA, the build proceeds along the Z direction. Therefore, for every layer, the table should move in the negative Z direction. It goes down by the required layer thickness, which is again determined by us. And new liquid layer is recoated either by deep dipping for the case of SLA or for top fitting for the case of Zephyr. Now the beam scans the liquid layer for each loop. So just like any other AM process, as we discussed, the way the contour and areas are filled is that first there are a few contour passes, say 2 perimeter passes. Recently, I observed that for the metal 3D printing facility that we have here at IIT Bombay, the inner contour, or if you have 2 perimeters, the inside perimeter gets scanned first, then the outside perimeter. And this will typically happen with, in the case of SLA, with a laser spot of finer size. And why this is to preserve the geometric accuracy of the build. and then you fill the infill region, typically with, say, a zigzag or any other pattern of your choice, with a suitable step over or head spacing. And this can be done with a laser spot of a larger size. Now, this might be possible in the case of SLA, where you can actually say change or flexibly adapt the laser spot size itself. However, for other processes, such as say a laser-based YDD process for metals, often the spot size of the laser will be fixed, and thus such an adaptation is not really available to us. So, as we were discussing, for each loop, first the contours are scanned using a laser of fine spot size to preserve geometric accuracy, and then the area filling is done utilizing any contour filling area filling method which is most suitable. The outer contour is scanned with a small dia beam. Area filling is using a large dia beam. Now, after all the layers are made, the table rises completely, revealing the part. This was shown in the video, which Professor Kapil shared during his lectures, where we saw that initially, after each layer, the build table kept going down and down, and the entire part was dipped in the resin. But once the build was completed, the table rose fully to reveal the part, and then the excess liquid, which might have gotten entrained or entrapped because of the dipping of the cured part inside the excess resin, is removed or drained. Then the part itself is removed from the table, and the support structures are carefully taken off. Now, care must be exercised in this case because, as we discussed, because of the printing of support structures, while it is always our endeavor to make them weaker than the build material itself, or to make them less dense, or to eliminate them altogether, sometimes the support structures might be projected onto the part itself, and then you have two surfaces of the part which from which the supports have to be removed. Or in other cases, where the supports are subtended only on the build plate itself, where you still have one surface of the part to which the support structures are attached and must be removed from. It is possible that even after removal, some remnants of the support can remain on the surface, which can degrade the surface quality, or which might require some additional effort and time on our part for complete removal. Also, given that we mostly work with polymers in the case of SLA, the structures are really not as strong as, say, a metal or a ceramic based part. And thus, while removing the uh, support structures, say using some metallic knife or some implement, it is also possible that we end up damaging the uh, main build structure itself. Thus, care must be exercised. The part is then kept in a post-cure apparatus where it is kept under UV radiation to complete polymerization. What is the need for post-curing if we are already curing it using the UV laser inside the SLA machine? Now, the idea is that, as I said, we want our support structures to be weaker than the build material. One way to realize this is by, say, making them less dense. One way is to use a different material. However, that is not possible in the case of SLA, where the entire vat is filled with material, which is that only one resin. So what is done is it is only partially cured in the sense that the material is not cured to the extent that it becomes fully strong. And thus, both the build part and the support structures are weak. The support structures will be comparatively weaker because they will also be less dense than the build material or the build region. And then after the removal of the support, this entire part is kept under, uh, say, a UV chamber where the further curing occurs. Also, as we know, for the case of SLA, the beam is only scanned in the form of small regions along lines, whereas during the curing in the UV chamber, we can use a floodlight, a UV-based floodlight, to illuminate the part from all sides, and thus we can save a lot of time. These are the two primary motivations behind this step. Then the part is finished, and may even be painted if required. Here are some advantages and limitations of SLA compared to other additive manufacturing processes. In the context of AM processes, it is among the fastest and among the most accurate. It is fast because of the tiny moving parts, that is the galvanometers, which are actually used to deflect the laser beam across the region of interest. These galvanometers consist of a pair of mirrors which are attached to motors, and they are mounted along orthogonal but non-intersecting axes. Because these mirrors are very light, they have tiny inertia and thus they can be moved very fast, which means that the area of interest or the region of interest can be scanned at very high speeds. Typically, these speeds are of the order of say 10 meter per second. Higher speeds may also be achievable, but that is not always desirable, and why that is, we'll look at further. It is most accurate because the build layer heights can be really small. Also, given that it is the first system that was commercialized and even the first system that was invented in the context of AM, it has already been fine-tuned and has been thoroughly researched. Thus, the parts that you obtain from it often may not even require much post-processing apart from the removal of support structures, and the build quality is phenomenal. It can also be used to make transparent parts with fine surface finish based on the type of resin that you use. And another application of stereolithography, which is in the form of quick cast. It's a model which can be used for producing castings of any metal. However, all is not rosy. There are certain limitations to this process. It is very expensive. I mean, all AM processes are cost intensive, especially if you consider process like SLA or powder bed fusion or direct energy deposition. Some like FDM because of their wide adoption and because of being equivalent of desktop printers have seen great reduction in their costs with time. However, SLA still remains prohibitively costly. The parts do become brittle over a period of time due to continued polymerization through ambient light. We are aware that even ambient light that we receive has some UV radiation in it, and this UV radiation can continue to expose and contain can the part built by SLA can continue to polymerize even under ambient conditions after it is removed from the SLA system or the UV curing chamber. Because of this continued polymerization, the parts tend to become very brittle and can suffer fracture. Only photopolymers can be processed via SLA. It cannot uh, really be used for processing of same metals, and the process does involve the exhaust of hazardous fumes. Thus, it is not suitable for a desktop or office-like environment. It must be handled carefully. We have already looked at the various subsystems. We'll just touch them briefly. As we know, a UV laser beam is used as the energy source. The power density of the laser spot and the material properties are the factors which govern the curing process. We'll be looking in depth into the curing process today. We'll also be solving a few numericals based on the curing process dynamics. The laser beam is positioned during two small mirrors. The pair is called a galvanometer, which deflect the beam in two directions at great speeds. The recoating system in the case of SLA is deep dipping, which is also shown here. So once a layer of material is built or scanned, the stage will go down by a good height, which will be more than the layer height required for the next build. And this will lead to turbulence inside the resin vat, and the liquid from the surrounding regions will come on top of our pre-built part. This step is called as deep dipping. Then the stage will rise up again, and apart from the column or the height of resin required in terms of the layer height, the excess will be removed from the region of interest using something called a roller or a doctor's blade. Then this next region can again suitably be scanned, such as shown here. This week we were also introduced to some basics of lasing action and lasers. So as we are aware, it stands for light amplification by the stimulated emission of radiation. Light is defined as any electromagnetic radiation which has dual nature of both waves and particles. And if we are treating it in the particle sense or the classical sense, a particle with light energy is called a photon. In vacuum, all electromagnetic radiation travel at the same speed. However, the frequency and wavelength are different. Because of this difference in wavelength, they interact with materials differently. Such as we are aware that CO2 lasers are suitable for processing ceramics, or recently it has been found that blue lasers are suitable for processing copper. If we use a typical laser, such as one with wavelength of say approximately 1 micron or around 1000 nanometers, these will not be, while they are useful for printing say steels or nickel based superalloys or even titanium alloys, they are not only suitable for printing copper because every material has an absorptivity that varies with the change in wavelength. For wavelengths of the order of 1 micron, copper and aluminum have very poor absorptivity. However, this can also be mitigated by a change in temperature because we know that even the absorptivity is also dependent on the temperature. However, it has been found that by the use of blue lasers, which have a lower wavelength, say somewhere of the order of 400 to 500 microns, the copper has good absorptivity of this wavelength of laser, and thus even without any need for preheating, the blue laser itself can be used for printing copper. Thus, we often encounter situations where we see that the interaction of the electromagnetic radiation with different materials will differ based on the type of frequency and wavelength of the radiation. In the case of SLA, as we are well aware, we typically work with UV lasers, which are in the ultraviolet region shown here. Now, lasers have the property that they are monochromatic, that is, laser all beams, throughout the cross section of a laser beam, the wavelength will be constant, it will not vary. For example, we know that white light consists of all possible colors or wavelengths of light. Also, the laser beam is highly coherent. And what this means is the laser beam travels in the same direction. And all the waves which compose the laser beam are in phase. As we are aware, typically, it might be possible that we have two waves and there can be some phase lag or phase lead between two waves. However, in the case of lasers, they are all in the same phase. And thus, they can say interact with each other to provide greater intensity of energy for the same region. Also, they're all traveling in the same direction. Whereas in the case of other examples, such as an LED diode shown here, we see that while the light may still be monochromatic, that is, it may still be of one color, the light waves are actually traveling in different directions. And even if by chance they might be traveling in the same direction, they need not necessarily have the same phase. Thus, they are not coherent. Professor Kapil also touched upon the principle of lasing action, so I will not discuss it again. But basically, it operates via the mechanism of population inversion. Before that, energy is pumped into the system, and after population inversion, any further input of energy leads to the spontaneous emission of radiation. We're also aware that a lasing system consists of a fully reflecting rear mirror, and on the output side, we have a partially reflecting front mirror. The interesting thing to note is actually the transverse behavior or the transverse section of the lasers, which is denoted by notations such as TM00, TM10, and so on. So the two spatial modes of any beam are the longitudinal mode, which is visualized here. That is within a given length, how many modes the vibration or the wave can take, and the transverse, which is actually visualized here. That is when you cut a beam and you're looking at the cross section, what are its characteristics? What do they look like? Both of these modes are in fact independent of each other, and the transverse dimension in a resonator is normally considerably smaller than the longitudinal. As we're aware, just like for any other wave, the wavelength, say in this case, the distance between successive peaks of this same wave. So if we are tracing this wave right here, or even between successive values, they will be the same, is the wavelength. And based on the mode number, and n times the wavelength shall equal the length of this resonator. And the transverse electromagnetic modes, or the TEM modes, describe the shape of the energy distribution in the beam cross section. So it is not necessary that always the beam cross section will have uniform distribution of energy, such as shown here. It might also be possible that there are some regions, such as here, which is not illuminated, or a region on which energy is not incident. Thus, if we were to use a beam of this shape or of this cross section to scan any region, we might find that even in a single bead, so if you're looking at the top view of a bead, you have regions near the edges which are cured properly, but there is some region in the middle which is uncured, or where the resin is still in the liquid form. Similarly, these modes can be modulated to produce different energy distribution of beam along the cross section, and the typical nomenclature is EM XY. X will point to the number of non-illuminated regions along the x-axis, while similarly will point to the number of non-illuminated regions along the y-axis. In the case of TM00, along x-axis there are no non-illuminated regions, along y-axis there are no non-illuminated regions. So assuming a beam of circular cross-section, you have the entire region illuminated. Similarly, for a TM10 beam, there is one region in along the x-axis which is not illuminated, and we may assume that the distribution of the energy is symmetric around this region. Of course, that need not always be the case. The distribution of energy may also be asymmetric. Similarly, for the case of TM31, so if we were to consider this, TM31 signifies that there are three non-illuminated regions along the x-axis. So say you started with a beam which was originally circular or close to circular, and then you modulated it such that There are these three regions along the x-axis where the energy is not incident or is somehow blocked. Also, the second subscript signifies that there is at least one region, not one, there is exactly one region along the y-axis where the energy is also not incident. Then you fill the remaining regions with the energy and you get the distribution. Of course, it might also be possible to use a combination of such modes to come up with new shapes, such as the donut shape in this case. Now again, those of us who are working in, say, laser-based processes or otherwise may still have heard that the distribution of energy along a laser beam is not really uniform. In fact, it varies along a Gaussian profile. It is high or along a bell curve profile. So it is the highest at the center, and as we move out radially, it decreases. However, there is no sharp boundary as one might see here. It appears that there is this sharp boundary, say at some RC, till which the energy is incident or the energy is distributed. However, as we know from the nature of the bell curve, it actually goes on from minus infinity to plus infinity, and there is no sharp boundary per se of the laser beam. Now, the mathematical distribution of a Gaussian beam is defined such: IR at any radial position R is equal to I naught times e to the power minus 2r square by w square. This I naught itself is defined as the power intensity for r equal to 0, and the parameter w is that magnitude at r for which the power intensity is a fraction 1 by e square of I naught. So w is equal to that value of r for which IR is equal to 1 by e square I naught. If we are given the total power that is input to the laser, that is, if we are given the value PL, then we can also derive an expression for the intensity at any radial distance r in terms of this total power. Now, the detailed derivations have been covered by Professor Kapil in his lectures. I will not be as thorough. We'll just quickly browse through the important formula which will help us in solving the numericals later today. The power in any strip which is a distance r away and dr thick is simply the intensity IR, which is assumed constant in the strip. That is, we are saying that over a distance dr, over a radial distance dr, this intensity will not vary appreciably times the area, which is 2 pi r dr. Basically, we take this strip, we cut it along any section, say here, and then we straighten it. It becomes a rectangle of thickness dr and length 2 pi r. So IR times 2 pi r dr, and to obtain the total power, we can integrate. Uh, we know that the total power PL is simply the integration of this. Okay, simply the integration of this elemental power over the entire region. So from 0, which is right at the center, till infinity, because as we discussed, the Gaussian beam does not really have a sharp boundary. It actually goes on till infinity. And this integral has been worked out to be this. So the intensity at any radial distance r is given as 2 PL, PL being the total power of the laser, by pi w square. W, as we know, is that value of the radial distance at which the intensity is 1 by e square, the maximum intensity, which is at the center, times e to the power minus 2r square by w square. Now, a laser beam after coming out from that lasing chamber is highly collimated. That is, the rays of the laser beam are parallel and do not converge or diverge appreciably over long distances. Its diameter does not change much since the rays are not converging or diverging. However, there is a slight divergence in the laser beam, which is defined by the beam quality parameter BPP. It is measured in terms of MRAD, and 1 MRAD is defined as 1 mm diameter of beam will become 1 meter, that is, it will diverge to 1 meter after traveling a distance of 1 kilometer. However, if beam is further processed or focused using a focusing lens, then the scenario will of course be different. We are aware that while the beam is highly collimated, it is still not really parallel. And when we say that we have focused the laser beam on our build plate, what we really want to say is that the waist radius is on the substrate or at a specified distance from the substrate as per our requirements. So the beam never really focuses to a point. That is, the rays will never really intersect per se. They will achieve a minimum radius and then will diverge away. This minimum radius is called the waist radius. For an ideal Gaussian beam, this waist radius may be determined as W naught equals twice lambda by pi theta, theta being half the angle of divergence as shown here, lambda being the wavelength of this irradiant energy. However, for a real beam, it is also multiplied by a factor of m square, which measures the beam quality in terms of divergence. Now, some numericals which were covered in class. However, we will cover numerical, which is more say like the questions that are posed in the assignment. Now, similarly, if we look at the curing of one single beam, the intensity in terms of watt per meter square on the top surface only they were defined as such: I is equal to 2p naught by pi omega naught square e power minus 2r square by omega naught square, and the total exposed energy per unit square area of the resin, again only on the surface, can be defined as E x y and z equal to 0 is integral of this intensity dt. Why we are talking only of the surface? That is because as the laser beam will penetrate below the surface, not all of the energy will be able to pass through. Some energy might get reflected, some energy will get absorbed in the initial layers of the resin, and this energy may further be used for curing of the resin. This is governed by Beer-Lambert law, which we'll also look at. If the energy is incident at one point only from time t1 to t2, then this energy can further be quantified in terms of this uh, definite integral. Now, if you were to assume that during this time from t1 to t2, the laser has scanned a single bead along the x direction, measuring from minus L12, and the length of the vat is taken as 2L. This is just for mathematical convenience. We can also integrate it from any choice of limit, say 0 to L or something. Then we can also obtain an expression in terms of the velocity and in terms of the x and y coordinates, which is given here. And we observe that the laser exposure is proportional to e power minus 2x square by omega square. However, in this case, the integral was between some finite limits minus L to L, and it might get tricky to compute this integral or the value of this integral between these areas. However, as between these lengths. However, as we discussed, the Gaussian beam does not really have a finite uh, diameter. It does not have a sharp boundary. And given that it varies with e power minus 2x square by omega square, This function falls off very rapidly with increasing x. Now, we use a term called the zone of influence to define what will be the useful region which may be used for computing this. Given that along a radial position, the energy of the laser beam, while distributed till infinity, but is mostly concentrated only in a small region. That region is called the zone of influence and defined as the zone where 99.9% of the incident energy is received. Outside this zone, only the remaining 0.01% energy is distributed till infinity, and the length along the x-axis of the zone of influence can then be calculated as such. We set the value of this exponential to 0.01% of the maximum. The maximum of this, as we know, will simply be equal to 1 when we put x equal to 0. And thus, the zone of influence, x dimension of the zone of influence, can then be determined to be 2.146 times omega naught. The typical beam spot radius for such machines may be taken to be of the order of 100 microns. Thus, for these values, the influencing zone or the zone of influence may spread from minus 214.6 micrometers to 214.6 micrometers, or essentially to 500 micrometers overall. Less than that, but the order can be taken to be of 500 micrometer. Thus, we see that 99.9% of the energy, the incident energy, is concentrated or distributed only in 500 microns. And thus, for this limit of integral minus L to L, there is one stretch of 500 micron where 99.9% of the value of this integral will lie, and rest will lie in the remaining region. So whether you take it from minus L to L, or you take it from minus 2L to plus 2L, or you keep increasing this minus 100L to 100L, or in the extreme limit, minus infinity to plus infinity, the value of the integral will not change appreciably. The error will only be contained in that 0.01% of energy that is changing. 99.9% of your incident energy is still concentrated only in a very small region. Just for mathematical convenience, we take the value of minus L and L as minus and plus infinities. And with this modification, we see that for a fixed x and for the surface, that is z is equal to 0, the variation of energy along the y direction can be computed as such. It is under root 2 by pi p naught by vx omega naught square, vx being the scan speed along the x direction, e power minus 2y square by omega square. Now, all these computations were made just for the surface, that is for z is equal to 0, assuming positive z downwards. When the laser beam is striking the resin surface, its energy is getting absorbed and the exposed energy is declining with the depth z. Now, this is governed by the Beer-Lambert law, and the available energy at any depth z can then be computed as E at yz for a fixed x is equal to E at y0 times e power minus z by dp. dp here is defined as the penetration depth, or the depth of penetration, and defined such that when the depth is equal to this depth of penetration, the available energy is equal to 1 by E times the energy at the surface. This can again be simplified in terms of the previously obtained expression for E at the surface. However, one consideration is that we may be scanning our laser across a single bead, and say somebody decides that They want to reduce the build time. They want to increase their productivity. So they will scan this at a very high speed. Will it always be good? Can we keep increasing the scanning speed monotonously or monotonically? Or will there come a limiting time such that the laser is scanning too quickly for any of the resin to get cured? This can be seen by comparison of the time scales, such as one done here. So say the time taken for photon to pass through a single resin layer of thickness LP is given by TL. So you have a layer of resin. I mean, you have a vat of resin. Inside it, you consider one thin layer of thickness LP, and the photon is incident on this. The time it will take to cross, let it be given by TL. Now TL is found to be LP by CR, where CR is the velocity of light in the resin. Pretty straightforward. And this will be of the order of picosecond. So 10 power minus 12 seconds. Remember, in scaling analysis, we are only concerned with the orders of the quantities because the actual values or the exact values may change with depending on our approximations. These errors can be pretty large. So for the sake of it, we do not really distinguish between say 3 picosecond or 5 picosecond or 7 picosecond. What matters is whether it is 3 picoseconds or 300 picoseconds. Similarly, let us look at the time scale for cross-linking of the polymer in a single layer of resin. Say, even if you are allowing the photon to pass through the single layer, is it passing too quickly for any polymerization to take place? Before the termination of the polymeric chains, has the photon already passed and taken its energy with itself? So typically, the process of cross-linking following the free radical generation takes the time, which is say given here by Tk, and this is typically of the order of microseconds. So 10 to the power minus 6 seconds, which is almost 10 to the power 6 times more than the time it takes for the photon to pass. Now, the time needed for laser exposure to reach 99.99% of its value when a Gaussian beam is scanned at a constant velocity past a given point is called the characteristic exposure time TE. Now, this time TE is typically of the order of 50 to 2000 microseconds. So this is a pretty big range. So on the lower end, it is of the order of some 10 into 10 to the power minus 6 seconds. On the higher end, this can be of the order of 1 millisecond. So 1 into 10 to the power minus 3 seconds. However, this time scale is still larger than the time taken for cross-linking, that is TK. Thus, we can safely say that uh, our scan parameters or our process parameters are such that it will allow sufficient time for cross-linking of the polymer to happen. However, what is the shape of the bead along the Z direction? That is, inside the liquid, how does the shape of the bead vary? As we can see here, it varies as a paraboloid. And this can also be seen for the from the expression for EYZ. So at a fixed x, if you are looking at the variation along the y and z axis, all the regions where the exposed energy has crossed the critical value for cross-linking polymerization EC will be cured, and such location can be obtained as shown here, which will finally yield an expression for Z of the form Z equals minus AY square plus B, which is nothing but an upturned parabola. So for your axis pointing upwards, it would have looked something like this, but our Z axis points downwards, so it's inverted. Similarly, we can find the maximum curing depth, also given by CD, and this curing depth, as we are aware, will occur for y equal to 0. So corresponding to this, y equal to 0, the Z max will be achieved, which is given by CD, and the expression for CD is also derived. It is equal to dp ln Emax by EC. Now these resulting CD values are actually obtained for a fixed maximum exposure and based on for a fixed or a given material. Now these values can be plotted along with the maximum exposures on a logarithmic scale to give a semi-log plot. Since the magnitudes of dP or the penetration depth and EC, that is the critical energy required for curing to occur, will be material constants for any given resin and for a given constant laser output wavelength, this semi-logarithmic plot should yield a straight line. Why a straight line and how it takes the form of a straight line, something like y equals mx plus c, was also shown by Professor Kapil. Now these plots are then called the working curves of the respective resins. So for a given laser wavelength and for a given material or a given resin, we can be supplied with the working curves, which will have the plots of CD and EC. And using this plot, we can work out our laser parameters. We can work out the process parameters. We can work out the bead size, bead depth, and other characteristics which may be useful for quality control. And such curves are made by extensive experimental efforts. Through single bead laser curing experiments, you perform a sufficiently large number of them, validate them, and these are typically conducted in the range of the curing depth dP less than the critical curing depth CD less than equal to 4 times the curing depth dP. Why in this region? Because in this region, this semilog curve will be a straight line. However, beyond this region, the curve need not remain linear or need not remain a straight line, and there can be significant variation. Thus, it is preferred to work in this domain only. For some wavelength and material combination, so laser wavelength and the resin material combination, a working curve is shown here. Trying to obtain a cure depth smaller than the penetration depth is undesirable because then your material will have weakly developed properties. It will be very weak. It will break. It might not even retain its shape. On the other hand, the working curve usually becomes non-linear when a cure depth much larger than 4 dp is attempted. So we attempt to work in this region only, that is dp less than cd less than equal to 4 times dp. And such deviant behavior is also illustrated here along with some possible mechanisms. It might be the case that outside of your preferred range, say if you extrapolate your curve, it should have gone like this, but then the steepness of the slope has increased. This is called super logarithmic behavior because it is exceeding the logarithmic behavior itself. The other extreme, of course, will be when your curve tips downwards and then the slope becomes less than the logarithmic behavior. This will be called sublogarithmic. Now, for the super logarithmic case, there are two possible reasons which have been well defined. One is because of optical bleaching with the incidence of radiation and curing. The partially solidified top layer may become transparent for the laser. which will lead to an increase in the penetration depth. Because while it was translucent, it was absorbing some amount of laser while transmitting the rest. Thus, a lower amount of intensity of the laser energy was reaching the bottom layers. Now, after solidifying, now that it has become transparent, it is allowing all the intensity of the laser to pass through. Thus, the penetration depth will increase. Now, since dP is the slope of the working curve, this will result in positive curvature of the working curve, as shown here. A second well-explored reason can be optical self-focusing. That is, polymerization results in shrinkage of the cured part, and hence density will increase, which will increase the refraction index as well. This increase in the refraction index earlier for laser rays or for photons which might have passed straight. Now, because of curing and the increase in the refraction index, they will tend to be refracted towards the center. As we are aware, when light is passing through an interface and the first medium has lower refractive index than the second, light bends towards the normal. Whereas if light is going across an interface from a higher refractive index material to a lower refractive index material, light bends away from the normal. In this case, it will bend towards the normal, and thus there will be a greater intensity of incident energy near the center line, leading to higher depths. Again, since the CD will be more or the DP will be more, the logarithmic behavior will increase with the increase in slope. The other case, as shown here, whereas instead of continuing along this straight line trend, there is a dip in your working behavior curve. This can be due to a phenomenon called optical scattering, whereas imperfections at the microscopic scale or voids in your print act as scattering centers. And in the previous case, your incident energy was getting refracted towards the center line. Here, the incident energy may get deflected away. Thus, along the center line, you have lower intensity of energy acting, and your curing depth can be lower than before. This will lead to a reduction in the slope of the working curve. Uh, a few more important formula which will be useful for the numericals. So, maximum width of the bead on the surface, let us be clear, can be obtained as Cw equals omega naught under root 2 CD by dP. Cw is directly proportional to the laser spot diameter. Cw is proportional to the square root of the ratio of the cure depth. So this is actually equal to omega naught. A ratio of the cure depth to the resin penetration depth. And for the linear portion of the curve, this ratio of CD or 2 CD by dP will actually range between under root half to under root 2. Again, we can find an expression for the scanning velocity itself, which will come out to be under root 2 by pi, P naught by omega naught, 1 by EC being the critical energy required for polymerization or curing, E power minus CD by dP. Again, we encounter the ratio of CD and dP, and we observe that the scanning velocity is directly proportional to the laser power for a fixed laser spot size and for a fixed cure depth and depth of penetration. It is inversely proportional to the spot size, keeping other parameters constant, and the laser scan velocity decreases exponentially with the ratio of CD and dP. Again, here we encounter something called step over or head spacing, which is basically when we are, say, printing two tracks, the center to center distance between these tracks, because we know that the tracks are not just straight lines. They also have some width. The beads will have some width. If you want to look at the cross section, say you have two beads, you also have something on the surface, and say your next bead is here. Let these be the centers of the bead. So your laser or your deposition head will actually be moving along these centers and also deposit some material laterally. And we measure this center to center distance. This is called the step over or the head spacing. Notice how based on changing the value of the step over, we can induce different amounts of overlap between successive beads. The overlap can be high or low. Typically, we use say some 30 to 50% overlap in metal AM so that there are no intertrack porosities or voids. If you want to cover a region of width W and length L with a step over of S, the number of passes in this case will be equal to W by S. Thus, the curing time can again be calculated in terms of the area to be scanned, the parameter K, which is nothing but typically the step over is expressed in terms of some multiple of the uh, laser beam radius. In the case of SLA, this need not be integral. So it need not be the case that you only step in terms of 1 W naught, 2 W naught, 4 W naught, or so on. This can also be a fraction. And in terms of the area to be scanned, this parameter K and others previously encountered, the time taken for covering this distance or covering this area has also been computed as A by K under root pi by 2 EC by P naught into E power minus CT by dP. Example problem has been solved here. We'll also be looking at example problems of our own. Now let us look at the concept of undercuring, overcuring, and others. So when you have multi beads, that is, you deposit one bead and you deposit a second bead with some amount of overlap, we see that now in each region, the energy is not just contributed by one pass alone. However, there is the contribution of multiple passes. This will lead to a change in the cure depth. So previously, the maximum was here, and just by the influence of these beads individually, the minima should have been somewhere here. But because of this overlap of energy in this region, we see that some extra amount of region has also been cured. The difference between the peaks or hill and the valley is called the undercured depth. That is, rather than having a profile which is flat, we actually realistically have a profile which has some perturbations, which is not really desirable. We have some mathematical formulations for the exposures in the hill or peaks, termed as EH, and in the valleys, termed as EV. The uncured depth can be calculated in terms of these quantities. Typically, for a good quality print, we want this undercuring depth or the difference between the peak and the valleys to be less than 5 microns. Such a condition is referred to as planar curing. And typically what you want to do is you might want to check for your given set of process parameters whether the consider of planar curing is getting satisfied or not. If not, you might want to adapt your conditions better or your process parameters better. And for a given value of penetration depth, which in this case is assumed to be 15 into 10 to the power minus 5 meter, we can find that the ratio of exposure or ratio of energy in the hills and valleys should be less than equal to 1.034. As long as this condition is satisfied, while there will still be perturbations at the bottom, for our practical purposes, we may assume that the bottom is flat enough to qualify as an ideal part and we'll not have to change our process parameters. This has again been shown how for a multi-bead printing case, how the contribution from the neighboring passes will affect any one point of interest. So we adopt a Eulerian frame of reference and we look at only one point and we see that how the neighboring energy passes will affect or will contribute to the energy at that particular point that has been computed here. And we see that how by changing the parameter k, which if we remember was step over was defined in terms of k times the radius of the laser beam, we can see how the final beat profile can be observed. So for k equal to 6, we have a highly varying or sinusoidal type of wavy type of cured interface. For k equal to 4, the gaps decrease. As we reach k equal to 1, our interface has a small curing depth, a small undercured depth. For k equal to 0.9, it is almost flat. Similarly, for k equal to 0.5 and k equals 0.1. Given that we know that our zone of influence is only between 2. Minus 2.146 W naught and 2.146 W naught, also in the y direction, we can modify our calculations and thus take contributions only from the passes which fall within this zone of influence. This is typically done using such a formulation where we find only the passes uh, denoted by n which fall within this zone of influence, and to simplify our computations take contributions only from these passes. That was for the hills. Similarly, we have a formulation for the valleys, and in this case also we take contribution only from the passes lying within the zone of influence. And for this given case and for this given set of material properties, we found that the ratio of EH by EV was less than or equal to 1.034 and that the planar curing condition is satisfied. Just a very brief introduction to multi-bead, multi-layer print. So typically when you're optimizing any AM process, how you do is you start from a single bead, you optimize the process parameters, then you go to single layer multi-bead, then you finally progress to a multi-layer multi-bead, just as we have done here. So in this case also, we will not deal in great depth, but we'll look at the concept of over curing. Typically for say processes like metal AM, we want a certain degree of dilution. That is, if this is your substrate, when you're depositing a bead, you don't want all of it to be deposited just on the surface. You want some of it to go inside as well. And based on your formulation, either say as the ratio of these heights or as the area of the bead and the diluted area, we compute something called dilution. And 10 to 40% dilution is in fact deemed necessary for processes such as metal AM to have good bonding strength between any deposited layer and the previously deposited layer or the substrate. We want some of the material to get diluted or mixed inside the previously deposited layer. We don't want our fresh deposition to be wholly on the surface because it might lead to poor bonding and poor mechanical properties. Similarly, in the case of SLA, say we first deposited this layer, then we came up with this second layer. The height of this layer was only till here, but we chose this height such that the curing depth was greater than this height. So CD is actually greater than the layer height. And what this leads to is that some part of the previous layer which was already cured is getting some incident energy again and may get over cured. Similarly, when we are taking this third layer, we are repeating this process. This H is same as the previous one. However, it is less than CD, and this some already cured or pre-deposited layer is getting cured again. And this is done to ensure that previously we observed that there might be regions. These are the hills, these are the valleys. So near these valleys, it is possible that there is a small region which may remain undercured because of insufficient energy. But by doing this, we ensure that there are no such undercured regions because the undercured region is now falling in already a previously cured region. There is very little chance of the liquid the resin remaining in liquid form in those regions. Thus, we obtain proper curing and strong parts. Now, let us take a short break, and after the break, we'll solve some numerical examples based on this formula that we just went through. Good evening and welcome back. So let us continue where we left off. So we'll now solve some questions which will be helpful in strengthening our concepts as well as will be helpful in answering the assignment questions for this week. So the first question dealing with the transverse electromagnetic mode of the laser beam as we just discussed. To obtain the intensity distribution in the cross section of a laser beam as shown in the figure which is here, a combination of TEM modes can be used. So select the correct combination. Uh, we can do this by trial and error and see what each mode looks like. So just for reference, so TEM XY, this means the number of non-illuminated zones along the x-axis. The second subscript means the number of non-illuminated zones along the y-axis. Now TEM10 would have one non-illuminated zone in the x and no such zone in the y. It will look something like this. 1 1 would have one such zone here, one such zone here. This is the zone along the y, this is zone along the x. So something qualitatively like this. And we see that if we combine these two, it's not really equal to the desired shape. TM10 and 01. Again, 10 being and this being the non-limited zone, 01 being. And here we see that if we were to say combine these, so you have this region, you have this region here, then this can very well approximate the required region which is given to us, which is of a donut shape. And as we also know from the slides, this is the correct answer. It's actually a combination of TEM10 and TM01 modes, which can approximate this donut shape of energy distribution in the cross section. Now we looked at a plethora of formulae, so let us solve some problems related to those. So this is the common data given for the next few questions. In an SLA system, a resin is used in a vat of size zero point 0.2 into zero point 0.2 into zero point 0.4 meter cube. Following are the other specifications of the system. A 1000 milliwatt laser with Gaussian intensity distribution is used to cure the resin. The laser beam reduces its intensity by 1 by E square. So we know what this means at a distance of 200 microns. So this is in fact omega naught from the center of the laser beam. Also now it is clear that this 1000 milliwatt is actually the peak power P naught or PL as you may see fit. It is desirable to have a maximum curing depth to be 3 times the penetration depth. So a relationship between CT and DP is given to us. The spacing between two single beams is 2 times the laser beam radius. This spacing or step over given by S is equal to 2 times laser beam radius given by omega naught. We know that the general formulation is S equals K omega naught. The value of K is given to us as 2. If we were to visualize this, how would this look? So say you have the laser beam radius, top view of the laser beam radius, and then this is the radius, of course, omega naught. You are given that the center to center distance between two successive passes of the beam is twice this radius. So you go one more radius away, but then you end up just drawing the beam again. Maybe this is more realistic. As you see that here you have zero overlap between the beams. However, the overlap in the final cured bead might still be there. Not in the case of SLA, but in other cases such as in FDM or wire DED, where the deposited bead is often wider than the laser spot radius or even the uh, feedstock wire or filament width. In this case, for S equals 2W0, this is the scenario which is presented to us. The working curve of this material and wavelength combination is also given to us. The cure depth here is in mil or milli-inches, and versus the exposure in millijoule per centimeter square. And now come the questions. Determine the value of the penetration depth dp in mils. Now I will just use the formula as given to us. You can refer to the slides if and when needed. We have been given a relationship between the penetration depth and the curing depth CD. We also have a curve for the cure depth CD versus exposure. So maybe we can correlate these. The formula given to us is CD equals dp into ln E max or the maximum energy minus ln EC or the critical energy. And thus we need to find dp. dp is unknown. EC for a material is constant, and we already have a working curve for CD versus Emax, which is given to us. So these two. So we have two unknowns, dp and EC. Let us write them. This, if we can come up with two equations involving these two unknowns, we can solve for both. Now let us have a look at the working curve again. And similar to the procedure which Professor Kapil described in class, if you were to take any 2 points, say I take one at 60, value of exposure 60, and corresponding to it, the value of the cure depth as 4.8, and we take another point, say at 100, exposure equal to 100, and the corresponding cure depth is 6 mils. For the first point, the coordinates are 60, 4.8. For the second point, it is 100, 6. So it's 60, 4.8, 100, 100, 6. Let us put these values in the equation. For the first one, 4.8 is equal to dp ln 60 minus ln EC. Second equation is 6 is equal to dp ln 100 minus ln EC. Let this be equation 1, this be 2. Now you can solve this in any way you like. I will simply say subtract equation 1 from equation 2, which will give me, so 6 minus 4.8 equals dp ln 100 minus ln ec minus dp ln 60 minus ln ec, which implies that 1.2 equal to dp ln 100 minus dp. So ln ec will get cancelled out, dp ln ec will get cancelled out, and what will be left with is dp ln 100 minus ln 60, which will give me 1.2 is equal to dp ln 100 by 60 or 5 by 3, which is equal to dp times 0.511. So we have 1.2 is equal to dp into 0.511, or dp itself is equal to 1.2 by 0.511 equals 2.3483, and the unit is mils. This is the value of the penetration depth. Now we have to determine the value of the critical exposure EC. This can again be derived from the same equation, so I'll just write it again. CD is equal to dP times ln Emax minus ln minus ln EC. Now we already have 2 points, 60 and 4.8, and 100,6 from the working curve. So these are nothing but Emax, CD coordinates. We also found dP to be equal to 2.3483 mils. So if we substitute any of these coordinates into the equation along with the value of dP, we can easily find the value of the critical exposure EC. So just for convenience, I will substitute say 100,6. You can also substitute the other point or any other point from the working curve. So that will imply 6 is equal to 2.3483 ln 100 minus ln EC, which will imply that 6 by 2.3483 equal to ln 100 by EC, which further implies that this comes out to be 2.555 equal to ln 100 by EC. Now we raise both sides to the power of, we raise both sides as exponent to e, which implies that e power 2.555 equals e power ln 100 by EC, and we know that from the properties of exponents, this can come here, this can go there, which will equal 100 by EC times to the power of ln E. You know that ln of E is 1, so this will simply equal 100 by EC power 1, which is equal to 100 by EC. Therefore, 100 by EC will equal E power 2.555, which comes out to be 12.8713, or EC can be determined to be 100 by 12.8713 is equal to 7.769. The units are in millijoule per centimeter cube, centimeter square. This is the required answer for this part, where we have to find the value of the critical exposure EC. The next question asks us to find the value of the max curing depth of a single bead CW. Again, we'll directly use the formula that has been supplied to us in the slides. This max curing depth is denoted by CW, which is equal to omega naught times under root 2 CD, or curing depth, by dP, the depth of penetration. Now, if we go back to the given data, we identified omega naught to be equal to 200 microns. So is given to us omega naught is 200 microns, and it is desirable to have a maximum curing depth. So the case we are working with of maximum curing depth, CD should be 3 times the penetration depth dP. So CD equals 3 dP. Now, using this information, we can find that CW is equal to 200 microns times under root of 2 CD by dP. The CD by dP is already given to us. So this is 200 times under root of 2 into CD is simply 3 dP, so CD by dP is 3. It's equal to 200 root 6, and therefore CW comes out to be 489.898, and unit is micrometers because omega naught was given to us in micrometers. This is the maximum curing width of a single bead. Okay, these questions might have been repeated. We are asked to find the maximum curing bead, width of curing bead, a single bead in micrometers. We have already done that. The next question: determine the scanning velocity Vx in meter per second. If we refer to the slides, the formula for scanning velocity is also given to us. Is for time, yes. This is the formula for scanning velocity in terms of the other parameters. So let us just recreate it here. Vx is equal to under root 2 by pi p naught by omega naught, 1 by EC, e to the power, or exponential minus CD by dP. And let us see what quantities are given to us. P naught, that is the total power of the laser, is given to us as 1000 milliwatt. Or just 1 watt. Omega naught we also used in the previous question. It's given as 200 micrometers. Which is 200 into 10 to the power minus 6 meters. The critical energy EC we just computed in one of the previous questions, it was 7.769 millijoule per centimeter square. And if we convert it to SI units, it will come out to be 77.69 joule per meter square. What remains unknown is CD and DP, but we have the ratio of CD and DP. This is given by the relation CD is equal to 3 dp. So again, we see that all of the required parameters are given to us. We can directly compute the value of the scanning velocity Vx. Let us do that. Vx is equal to under root 2y pi. E naught is 1. Omega naught is 200 into 10 to the power minus 6. EC is 77.69 exponential of minus CD is 3 dp, so minus 3. And if we compute these term by term as I have done, these will come out to be 0.7979. The second term comes out to be 5000. 1 by 77.69. Okay, let us keep it as it is for this step. And e power minus 3 is 0.0498. And if you multiply this out, this will come out to be 2.55 meter per second. Let me quickly verify this because sometimes I can get my calculations wrong. Please also solve these independently, and if you notice any discrepancy or calculation mistakes, please let me know, I'll correct it. Yes, this comes out to be approximately 2.55 meter per second. So this is the scanning velocity. As we were also told during the lectures, typically the scanning velocities in SLA can be of the order of 10 meter per second. And so we are within the uh, recommended or the typically encountered region. The next part is asking us to find the time for scanning the entire area of the vat. This was also looked at in the slides. So yes, if we are given an area which has to be covered or scanned using the laser beam with some given step over or hatch distance, the formula for scanning the total area is given here. So I will just recreate it. T is equal to A by K under root pi by 2 EC by P naught exponential CD by dP. Let us again write the values that are given to us. A stands for the area of the region. Let's look at the question again. The vat is of size 0.2 into 0.2 into 0.4. So these correspond to the X, Y, and Z dimensions respectively. So the area is 0.2 into 0.2 meter square. The area A is equal to 0.2 into 0.2 meter square. K, as we are aware, the step over S is defined as S is equal to K omega naught. Here we are given the spacing between two single beads 2 times the laser beam radius. Thus the value of K is 2. Pi by 2 is a constant. EC we already calculated in a previous subpart. So notice how without successfully solving one subpart, it is impossible to proceed to the next. And thus, if you encounter such a question in an examination, if you do not solve for one part, it's highly probable that you won't be able to solve for any of the parts. But if you get a wrong answer, all your successive answers will end up becoming wrong. This is 7.769. 7.769 millijoule per centimeter square. We also calculated this in joule per meter square, 77.69 joule per meter square. P naught was 1000 milliwatt if I remember correctly. So just 1 watt. And CD by dP is also given to us as 3. So again, all the quantities are known and we can directly compute the value for the time taken to scan the entire area of the vat. This will come out to be A is 0.2 into 0.2 is 0.04 meter square. K is 2 into under root pi by 2 into EC is 77.69. P naught is 1 and we have exponential 3. This again comes out to be 0.02 into 1.2533 into 77.69 and e power 3 comes out to be 20.085. And if I quickly multiply this, this comes out to be 39.114 seconds approximately. This is the time taken for scanning the entire area of the vat. The next question is asking us to determine the ratio of exposure in hills and valleys. So remember how for multi-bead or multi-track deposition, we saw that even the neighboring tracks or the neighboring passes of energy can contribute to the increase in energy and curing at one particular point, and how we determine whether any neighboring pass is contributing to my point of consideration or not is by looking at the zones of influence. So first we will determine the zone of influence. Again, the zone of influence is the region in which 99.9% of the energy is contained. The remaining 0.1% energy is contained within the rest of the region. And if we refer to the slides, for hills, again, what I mean by hills and valleys, I'll just draw it again. Say you have these successive tracks. I should draw them closer together and deeper. So the final uh, profile which will emerge out of this will have overlap of these energies and will resemble something like this. So here you have these peaks highlighted in red, and also these valleys, which are pointed out in green. And we have set out to find the ratio of exposure in hills and valleys. So for hills, we determine the indices of the neighbors which are lying within the zone of influence as n is equal to plus minus 2.146 by k. Remember here that k was equal to 2. This will be equal to plus minus 2.146 by 2, which will equal plus minus 1.073. So we'll pick all the integral values lying in this range. So we will select integers lying between minus 1.073 and plus 1.073. These integers are minus 1, 0, and 1. Thus, the energy, accumulated energy or the cumulative energy for the hills will be given by E at minus s comma 0 plus E at 0 comma 0 plus E at s comma 0. Now, at each of these regions, we must remember that the individual energy was given as at any given x on the surface the variation of E at a given x on the surface, that is for z is equal to 0, was given by E at y0 is equal to E max exponential minus 2y square by omega naught square. Let us substitute that here. The first term becomes E max exponential minus 2y is equal to minus s square by omega naught square plus E max exponential minus 2 0 square by omega naught square plus E max exponential minus 2 s square by omega naught square. E max is common to all of these terms, and let us accumulate the rest. So the first turns out to be exponential of again we can what is s? So s is given to us is k omega naught. Also the value of k is 2, so s is simply 2 omega naught. The first term comes out to be exponential minus 2 into s is 2 omega naught square, 4 omega naught square by omega naught square. The second term is simply 0. The third term is minus 2 into s square is again k square omega naught square, so 4 omega naught square by omega naught square. So Emax times exponential minus 8 plus exponential 0 plus exponential minus 8, and this comes up to be 1.0006 times E max. Now let us repeat this exercise for the values. So for values, we choose the index of the passes which contribute to the zone of influence by the formula n is equal to plus minus 2.146 by k minus half. Here the value of k is 2, so this is plus minus 2.146 by 2 minus half. This is equal to plus minus 1.073 minus half, which is minus 0.5. So we will select integers lying between minus 1.073 minus 0.5 to min 2 plus 1.073 minus 0.5, that is between minus 1.573 and 1.073 minus 0.5. So just 0.573. And what are the values of these integers? Minus 1 and 0. So for the values, we find EV is equal to E at s by 2 plus minus 1 times s comma 0 plus E at s by 2 plus 0 times s comma 0. And if we remember, for values or for any point y comma 0 on the surface, E at y comma 0 is equal to, just like the previous case, E max exponential minus 2 y square by omega naught square. Let us substitute that in this formulation. This is equal to E max times exponential of s by 2 minus s is minus s by 2 sorry exponential y comes here, so exponential minus 2. What is the value of y? The value of y is minus s by 2 squared by omega naught squared plus E max times exponential minus 2. The value of y here is s by 2 positive square by omega naught square. Again, we can take E max common and s is equal to twice omega naught as given to us. So minus s by 2 square is s square by 4. So minus 4 s square is omega naught. So into 4 omega naught square by 4 into omega naught square. plus Emax exponential of, again the same, so this will also be minus 2 into 4 omega naught square by 4 omega naught square. Thus we take Emax common and we have exponential of minus 2 plus exponential of minus 2, and this will come out to be 0.2707 Emax. So now we have computed both EV and EH. We have to find EH by EV. Or the ratio of exposure in the hills and the valleys. EH is 1.0006 Emax. 0006 Emax. E in the valleys is 0.2707 Emax. And if we work this out, 0.0006 by 0.2707, this comes out to be 3.6963 or so. This is the ratio of exposure in the hills and the valleys. The last two questions determine the undercuring depth. When the formula was supplied to us, we'll simply use that. Undercuring depth, also denoted by UCD, was a function of dP and ln of EH by EV. Again, look how if we had not calculated dP and the ratio of EH and EV in the previous questions, we would not have been able to attempt this. What was the value of dP that we calculated? So dP is 2.3483 mils. 2.3483 mils, and EH by EV, which is computed as 3.6963. And if we do this, point 696 ln of this is 2.3483 into 1.3073. This will come out to be 3.0700. The unit will be mils because the value of dP was in mils. You can also convert it to micrometer or meter. The conversion was supplied to us. This is the answer. And finally, we are asked to check if the planar curing condition is satisfied. Can we look at the undercuring depth and check if the planar curing condition has been satisfied or not? So the formal way is planar curing depth or the planar curing condition is said to be satisfied if the ratio of exposures in the hills and the valleys, EH by EV, is less than equal to 1.0006. 1.034. What was this value in our case? So in our case, EH by EV turned out to be 3.6963. Therefore, EH by EV in our case is actually greater than 1.034. Hence, the planar curing condition is not satisfied in this case. So, those were the numerical questions that I wanted to discuss. I hope it will help you in your assignments. I'm sorry I have exceeded our time again. So, thanks for tuning in, and I hope to see you all next week. And I hope you are able to solve your assignments and score well. Thank you.